So today we're going to be talking about something that really one of my favorite subjects, which is applying quantum mechanics to quantum computing. And I hope by the end of this talk, you guys are going to actually also enjoy this subject and not be afraid of buzzwords or concepts, abstract concepts that doesn't make any sense. And maybe start to believe that quantum computing is going to be a reality. It's a reality. It's a reality for physics. It's not a reality for engineer yet, but this is just an engineer problem, so it might just be a matter of time. So my name is Marina, and I finished my PhD in physics last year. During my PhD, I had the chance of working in several labs, including Los Alamos, Brookhaven, and NASA. And after graduating, I started working as a security engineer at Yelp, and very sweet job. We are hiring, so if you're interested in some sort of opportunity like the, security engineer, learn more about it, just come talk to me after the talk. So the agenda today is really simple in some sense. In a high level, I'm going to talk a little bit about quantum mechanics, how this whole thing started. Then we're going to go to quantum computing with that concepts. And we're going to finalize end the talk with some concepts on quantum key exchange, which is probably the most important thing that I want you guys to take from this talk. And it might take 2, 3, 4 minutes or 10, 11, 100 minutes. Who knows? We'll see. Some disclaimers. This is my personal view. Doesn't reflect my employer, of course. This is a physicist's point of view. Quantum computer has several branches, several point of views. There's several things going on, and this talk is is the physics view on that. I want you to understand the concepts, but there are a lot of things. If you guys are interested, there are a lot of other things you can learn about. Yesterday, for example, Jennifer Catherine Phoenix gave this really cool talk about the privacy issues that we're going to face when you start to have quantum computers. I recommend you guys take a look at this. Her work is really good. So I'm going to start off with a question that's going to blow your mind. What if we're all just a simulation? So one of my favorite physicists, dead physicists, is Feynman, and he was one of the first persons who actually started to talk about the idea of everything being just a simulation and what would happen if you had a quantum computer. What's the consequence of simulate the low level of reality? But that's what quantum computers do. They're simulating the lowest level of reality that you can have. So Feynman once said that in 1982, he said that to simulate reality in the lowest level, you would need a quantum computer. But if you think about it, the universe is actually a 13.8 billion years old quantum computer. So let's not get ahead ourselves. Let's first try to understand a little bit of quantum mechanics and how it's changed the way physicists and scientists in general start to look at the world. So back in the 18th century, it was really boring. There's nothing much going on by the end of that century, and one of the famous physicists at that time, Lord Kelvin, even mentioned that there's nothing else to be discovered in physics. Everything else is just more measurements, just more precise measurements. We're done. But he didn't know that there are a lot of things that still to happen, and this was before quantum mechanics. So a lot of weird stuff starts to happen when they start to measure more stuff, right? And one of them was what they call it later, the ultraviolet catastrophe. So back in the 18th century, they knew that light was a wave. They had the experiments, for example, the double slit experiment, and they were pretty sure the light was just a wave. It could just reflect this in the wall and have all the properties that a wave has. And they knew that there would be a spectrum, and light would just be this wave and all infinite possibilities of wavelengths or frequency. So they were pretty sure that that would be all, and that would be done. But there's one problem, though. There is one. So if you go back to classic thermodynamic, all the intensity of what they would call black body, but black body is just something that emits more than the receiver. For example, the sun is a black body. So the intensity of a black body, was in the classical physics was thought to be just proportional to the wavelength or the frequency at some temperature. But if this is true, if this black body is emitting all infinite possibilities of wavelength, what do you think would happen if you, for example, if you like just have some fire on the beach, like you just start some fire pit. If you have this intensity, this black body intensity radiation emitting in all the frequencies, at some point you'd have so much intensity in your eyes that you'd just be blind. You'd have all the infinite possibility, and that was really weird. But mostly, they start to see that the classic idea that they have in thermodynamics didn't match with the experiments. So basically, in the classic idea that it would have all this intensity, this continual intensity of wavelengths of frequency just increasing with temperature, would have something like that line over there. If you decrease the wavelength or increasing the frequency, you'd just have your intensity going to infinite. And that doesn't happen. We don't see this in reality. Actually, what you see is some sort of these weird curves that variate to each temperature. And the scientists didn't know why this was happening at that time. So Max Planck, really smart guy, in the very end of 18th century, asked his friends, pointed to the scientific society, what if the energy was actually released as bundles instead? I don't know why, but what if it's just not continuous? What if it's just somehow quantum, little pieces bundle that he called actually quantum? And he came with this law that it was a completely empirical law. He didn't know why, but he was able to actually predict that curve that we saw in the previous plot. And he came with this constant called the Planck constant. Instead, the energy would be just proportional to this very little, very small values that empirically he found as being that value. Yeah. So, but he didn't know why, right? So 5 years after that, Einstein came with an idea that actually was the biggest revolution in quantum mechanics. And most of the people think that Einstein actually got his Nobel Prize because of relativity, but it was actually because of the photoelectric effect. And what is this photoelectric effect? So at the same time that Planck was having that weird idea of maybe the light was in bundles and we don't know why, there's this experiment that was also really weird. Basically, they were pointing light to some metal plate, for example, potassium, and if you pointed just like low frequency, for example, just red, to this plate, you don't have any electrons come out. But if you increase your frequency, you'd see some electrons come out. It doesn't make any sense, right? What they were expecting that time is just if you have like very low frequency, it would be just some few electrons coming out with like very small energy. But what happened is just they didn't see anything before a threshold. And they didn't know why. So Einstein actually had this crazy idea that maybe the energy, maybe light actually wasn't a wave. Maybe it was also a particle. And he called this photon. And he used a Planck constant to say that this photon would have energy proportional to the frequency and the Planck constant. So it was a really simple equation, and he got the Nobel for that. So it took 20 years after that to then realize that maybe everything is also is a particle and a wave. So de Broglie in 1924, and this was in 1905, came with this idea that maybe matter also could be seen as a wavelength. And again, we have the Planck constant, and you see this wavelength is actually inversely proportional to the momentum. So we are in the world that everything is actually a wave and a particle. And the way physicists study this, the way physicists can deal with this weird property of matter and energy is postulating that we can describe matter as a wave function. So basically, a wave function is a mathematical probability that represents the quantum states of each particle. So this is one way of representing, for example, in this case, this is a wave function of one particle in the box. This is one way of representing this wave function. There are several ways you can use several different bases. We show linear combination of two states. And if you look close to this equation, you see that there's A plus and A minus. This is the amplitude. So the wave function just like this doesn't mean anything physically. So to go to the physical world, to go to some point that you actually can see something, you need to go to a point that you can probe something. You need to you can't have like you don't want just you need to go to okay, sorry. So this is just a mathematical way of express the wave function. You want to probe this, and the way you probe this, you just square and take the models of that. And when you square, you see that we have like these little functions, the exponential functions. This is actually sinus and cosinus, right? When you square this, you only get the amplitude from that. And the amplitude says what's the probability of having this particle going either left or going either right. The little amplitude over there, A plus and minus, that's what we are seeing. That's what the physics show to the scientists. The other way you can also express your wave functions, is, for example, with this notation bracket. And that's important because that's what you're going to use in quantum computing. So in this case, we are represent the state of a photon or some particle as either in the base, either in up or down. And these are orthogonal bases. And by the way, if you remember Shor and the equation, and maybe you were familiar with the Shor and the cat, you know that's what they meant. Like the wave function is just a solution for Shor and the equation. And when you mention that the cat is dead or alive in the box, all you're saying is just a superposition of a state of alive and dead. And the amplitudes, in this case, if you look, there's a 1 over square root of 2. This would be the amplitude. If you square this, as I said before, that's when you square the amplitude, you get the probability of your measurement. When you square this, you're going to have one half. So it's half dead and half alive. That's the idea. So again, what happens if you open the box? If you look if you want to see if the cat is dead or is alive, before you open the box, you can be dead or alive. You can have a spin up or spin down. You can have a state 0 or state 1. But once you open the box, once you look, you probe, you put your probe there and want to see what's happening, you need to, the probability collapses to just one state. So you either going to have up or down. Or you either going to have 0 or 1, or dead or alive. So all right, let's try an experiment. Let's try to see if you can actually grasp this idea better. Suppose you guys have 3 Polaroid filters. You can there's some sunglasses that are polarized, so you can just grab 3 sunglasses that have this property and just turn turn them around to have the polarization horizontal, vertical, and 45 degrees. And then you shine the light in one of them. What happened? Okay, if you shine the light in the horizontal Polaroid, you're actually measuring. That's what you calling probing. You're actually polarizing all the light everywhere before you actually probe this. The light isn't ever possible polarization. But once you inside this in the polarized, once you look through this, you're gonna, if for example, if you have the horizontal filter, all your light that comes from this filter is gonna be polarized in the horizontal. Now you place the second one, the one that is vertical polarized, in front of that one. What happened? All the light comes from the first polarizer or horizontal polarization. But after that, if you post a vertical polarizer, you don't get any light come out from that, because all your light was horizontal. Okay, no big surprise so far, right? It's just you polarize first in horizontal and then vertical. But the magic happens when you actually place the third polarizer, the 45 degrees polarizer between them. If you do this, you actually start to see light coming from the third polarizer. And that's the crazy thing about quantum mechanics. Do you guys realize this, or do you guys realize how weird this is? You had no light coming from that, but you just placed a 45 polarized, which is actually another base. It's a base in 45 degrees. You place this in between, and you have light coming from that. So basically, what happens is the following. These are two-state bases, right? You had the first base was horizontal and vertical. This is two states. They are orthogonal. But the 45 degrees is actually a linear combination of these two bases. So we actually have the two states. We have horizontal and vertical state inside this 45 polarizer. So when you place your 45 there, what happens? You're actually taking you choosing one state. You're choosing the state, the horizontal state. But you actually you are a linear combination. You are a linear combination of vertical and horizontal. So that was your wave function in the beginning, right? It was you choose this base, horizontal and the vertical. But if you choose to change the base, which is just again a linear combination of the other base. For example, you can express vertical as just 45 degrees, a combination of 45 degrees in each side. And these two bases over here, they are also orthogonal between them. You just change the base. So once you place that second polarizer in the between, you actually change the base, and you have one half of chance of have a vertical polarization, and that one half goes to the third polarizer, and you see light. That's what quantum mechanics is you can code a lot of information in something in some wave function, and until you don't look at it, you have all the information there. So now we are ready to actually talk about qubits, right? So qubits is this idea of represent a two-dimensional state of a particle, for example, a photon. But as I will show later, it can be actually several other things, not only photons. All we need is just a two-dimensional state. And this complex vector space is actually the Hilbert space. So you want a qubit, you can just choose another base for your qubit. You choose a base that you're going to call 0 and 1. And again, summing these amplitudes, the amplitudes, the square of each amplitude should be 1, because this is the probability, right? So remember I was saying before, there's 1 over square root 2, and you square this is 1/2. That's the chance that you have, a chance of having that measurement of being dead or being alive. And this should be sum 1, because we talk about probability here. And another way you can see a qubit is just look to the block sphere. Think about this. Think that your qubit is just a point in that sphere, and you have all the possibilities, any possibility of being in any point of the sphere. So you actually you're encoding all the two-dimensional space in your qubit, and you only know what you're measuring if you're 0, 1, the moment that you actually probe that. Until you probe, until you look at, you have all the possibilities. You have all that information encoded in your wave function. So this is for one. That was for one qubit, right? What if you have two qubits? This is going to be you're going to have a tensorial multiplication, and you actually end up with 4 possibilities of states, not only 2 anymore. What if you have 3 qubits? You add one more state, and you're gonna have all this information. Each of them encode one possibility of information, one possibility of calculation. And now you scale for 4, 5, 6 qubits. So if you have all this information, is going to be just encoded in one wave function. So basically, what I'm trying to tell you is just that quantum mechanics give us these spooky particles that can encode and do multiple things at once, just like a parallel machine, a massively parallel machine. So now we can go to Shor's algorithm. That's probably one of the breakthroughs from quantum computing. So we all know that public key crypto relies currently on just in the difficulty of factoring like fracting large numbers, right? So we have RSA, elliptic curves, and this is just because mathematically it's hard to factor these prime numbers. But in 1994, Peter Shor actually showed that you can use a quantum computer to find these prime numbers in just few milliseconds. So if you think about, I'm going to explain a little bit how Peter Shor did this, but let's just stop a moment and think about it. In the moment that you have a quantum computer, all the internet is broken. Everything is gone. Everything is broken. And remember, we don't have forced secrecy with those protocols. So everything 10 years ago, everything's going to be read. Everything's going to be available. So Shor algorithms, basically, one thing I forgot to mention from when you were a student in quantum mechanics and look into the qubits. So I show you guys that you can just couple a lot of qubits together. But every time you add more qubits, you're actually adding 2 to the number of qubits, possibilities of calculation at the same time. So for example, for a 100-bit number, all we need is just have 100 qubits together. And you don't need this for like long time. You only need this for a few seconds, and your calculation is done, and you have your results. This is again because the wave function will encode this into 10 possibilities or states. So you might think, okay, this is like super weird, not gonna happen. It's probably super hard. But then you start looking to the papers and look to what the community is doing. And for example, this is like in November. And they were able to factorize 56,153 with only 4 qubits, right? This is like a few months ago. And just so we can have like an idea what's going on. So Shor's algorithms use this a different kind of adaptation for a Fourier transform. Fourier transform is like a great friend of all physicists. We use this to actually move from one dimensional space to other. For example, if you want, you can use this to look to peaks, to look to your data and see where the important data is. So Shor adapted this and call it quantum Fourier transform. And basically what happens is just this algorithm just runs simultaneously in the same time every part of number. And the wave functions are just going to either sum together or just cancel each other. In the end of this calculation, the right numbers, the prime numbers that we're looking for, are going to be peaks, because they're going to be just waves that add with each other. And these peaks are actually the frequency, and then you have this you have the period of you have the period of your prime number, and from that you can just factorize this very quickly. So, all right, so this is really scary. But there's more. There are actually good news. We actually can use quantum mechanics to create and distribute key. And that's what I want you guys to... That's actually the most important thing about this talk, I think. And I want you guys to understand it, because it's really beautiful. So what Alice and Bob are going to do, they're going to distribute qubits through a quantum channel and to establish this key, as I'm going to show later in the next slides. And then they can use this key to just communicate in a classical channel. So the way it works is just quantum computer security is based in one of the most famous, most interesting principles in quantum mechanics, which is the Heisenberg uncertainty principle. This principle is encoded in several ways. You can say that there's are two of them. And what they mean is just you have a little uncertainty in your moment, and a little uncertainty in your space. And if you try to really close your space, you lose your moment. You don't know what's the moment of your particle or velocity of your particle. And for energy and time, the same thing. If you want to measure the energy of your particle, you don't know what time is happening anymore. And this is all bound on Planck constant again. It's a little bit more complicated than that, but that's like the high-level description of that, of the Heisenberg uncertainty principle. But for quantum computing and quantum crypto, what you want to is the idea that you cannot make a perfect copy of a quantum state without disturbing it, without introducing errors in your communication. And that's what you're going to use. So quantum crypto is something that's secured by not math, but physics. Alice and Bob now can exchange their quantum encoded key in a secure channel. For example, in the photons and fiber. But let's see how this works. But first, because of the Heisenberg principle, if Eve tries to read the state of the photons, the probability collapse. Remember I told you when you look at the state of your Wavefunction, you collapse that probability to one state. So if Eve tries to read whatever communication Alice is trying to send to Bob, Eve is going to collapse that wave function to one value. And Alice and Bob will be able to detect that happened. So the first and the most simple protocol for quantum key distribution is called BB84. And it's not that complicated. So basically what happened, Alice prepares a sequence of photons. And this is an engineer problem. And it's not that hard at this point. People are actually able to do this. And again, the only thing you need to make sure is just that you have only one photon each time. Because if you have two of them when you're doing this one photon each time with a sequence of time, if you have two at the same time, you can actually encode the same information. There are some properties in quantum mechanics that encode the same information, there's two or three or more photons. So all you need is just prepare a sequence of one photon each time and polarize them with... So Alice can polarize this with any base that she wants. Remember we talked about two bases, one that's horizontal, another one that was vertical. No, one that's horizontal and vertical, and another one that was 45 degrees this side, 45 degrees that side. These are two different bases, right? They are orthogonal between them. So Alice just use any of these four bases, any of these two types of bases, and just prepare her photons and send this. So she has a photon, she put the one base, vertical, horizontal, whatever she wants, or 45 degrees, and send. Another photon, she polarize in one of these bases and send. So she just sends several photons and a base, some state that she knows. Bob measures these photons, and he doesn't know which bases Alice was using, but he just chooses like any of these four possibilities too. And once he measured this, these photons that Alice sent to, but in his own base, he actually probing this, and he actually has a result, and he has either 0 or 1. For example, they can agree that up is 0 or up is 1, and down is 0, and up is 0, horizontal is 0, vertical is 1, or 45 degrees this side is 0, and 45 degrees on that side is 1. So he measures all this, and he gets these bits, and he keeps these bits in secret. And after the whole, after this all ends, this is going to be the key. And they both, Alice and Bob, are going to have the same bits. And there's going to be a key that they share. So after Bob measured, Alice and Bob just talk about the bases, but not the bits that they used, and they discard the base that they measure wrong. So again, Alice is choose for each thought one of the four possibilities of the two bases and send. Bob doesn't know what base she chose, and he also pick one of these four, and he measures, and he has some bits. And then they talk, I don't know, by phone or something, or email, and they say, and agree, and tell each other which base they measure without telling which results they got. And the base that they didn't agree, they just discard. The base that they agree, the bases that if they use the same base to measure that photo, they're gonna have the same result, either up or down or 45 degrees. They're gonna have the same value. So they're going to have the 0 and the 1. They're going to have the same key. So this is a little bit abstract. So let's try to put this in a picture. This probably is the most important slide of this talk. So if you pass through this, we are all right. So like I said, Alice has four possibilities in two bases, right? 45 degrees, or horizontal or vertical, and they agree that one is 0, another one is 1. So Alice has all these photons polarized in any direction. She measures in one of these bases and sends to Bob. So you see the first one was polarized and vertical, the second one horizontal, and then 45, and so on. And Bob has the same four bases, but now he's just actually probing this. He's not prepared. He's not polarizing. So he either probe this in the 45 degree base or horizontal or vertical base. And once he probes this, if he's probing the right base that Alice sent, he's gonna have the same value that Alice had. So if Alice sent, for example, 1, which is a vertical value. If she polarized that photon in that direction, and Bob measured it with this right base, which is horizontal or vertical, Bob is gonna get 1 all the time. Like that's what he's gonna get. But if he measures with the wrong base, the one that's 45 degrees, he can get either 1 or 0. Remember, it's a superposition, right? So after Bob measures all the photons that Alice sent, they're probably going to agree on 50% of the photons, right? Because half of the time Bob is going to just not use the right base. But this is all right. This is good. It means that half of the time they have exactly the same key, and they know that because they know which base they measured. So they can just discard the other ones, and they have a key. So what happened if Eve actually tries to measure these photons? So once Eve tried to measure any photon that Alice is sending, she's going to have to probe this. She's going to have to use one of those detectors over there, and one of the two types of base, either 45 or vertical horizontal. She's going to have to actually use this to probe, and she's going to collapse the wave function to one value. So, for example, if Eve, the same thing that Bob did, but now she's probing, and then what happened if she used the wrong basis? It means that she has 50% of chance of getting, for example, if Alice sent the photon polarized to one to a vertical polarization. If Eve choose the wrong basis, the 45% base, and measure this, she has 50% of chance of getting the right answer, which is vertical or 1, and 50% of chance of getting the horizontal one. So it means that she's interfering in that. She's actually adding a 50% of error in these photons. So in the end, when Bob tried to measure this after Eve, he's gonna realize that only 25% of all the photons that Alice sent are actually in agreement. And how do they know this? Because without actually talking about the bits? Well, you can just send several paired bits, for example. You could just choose some part of your photons that they're going to be just for testing, just to verify if they are right or wrong. And again, you're going to be sending like several photons. Much more. It's not only like 10 or like this. We're talking about probabilities, so it will be thousands of photons. So the whole thing is like, the whole point of this is just, in the end, if Eve is looking at it, they're going to have a really high error in the measurement, close to 25%, for example. And if Eve didn't actually eavesdrop that, would be at most around 50%. It's just a probability, but if you have a lot of photons in the end, you're actually able to know what's going on. And again, you can always agree to increase your probability. Alice and Bob could agree to increase the probability more than 50 if they want to really make sure. So, okay, this is very esoteric. Does it work? Well, people are actually doing this. There's several experiments. This one was a few months ago in Canary Islands. They were able to send several photons over 2 islands in Canary Islands, La Palma and Tenerife. And they were apart around 90 miles. And they were able to do this. They had like an entire key, and it worked. So, all right, so this is all super cool. But how long is it going to take to the first quantum computer? Well, there's some challenges, and again, just engineers' challenges, because the physics is out there. Quantum computers must maintain hundreds of qubits together, right, for some amount of time, like I mentioned at the beginning of the talk. You just need, like, actually a very short time, but you still need a lot of qubits together. But there is something that happens when you have all these qubits together. It's really hard to isolate them, because the universe is observing all the time. And when I mean this, it's just there's interference. Everything around you is actually, everything is interacting with each between. All the particles are interacting. So it's really hard to actually isolate these qubits. All this, and when you increase the number of qubits, it becomes even harder. Particles are just absorbed by the room or vanish, and several things happen. And this is actually what happens. Just this is a little bit a part of the discussion, but what happens just so you have a vacuum that's always the vacuum that is beyond everything, all the particles. This vacuum is actually very active, and they're creating and destroying particles all the time. And that's actually a field of quantum field theory. But anyway, let's not digress too much. So even though it's really hard to do this, there's a lot of progress happening. And in 2012, a Nobel Prize was given to two separate scientists who actually had two different solutions for this problem. One was an ion, a trap, and another photon, a qubit. And these are different particles, but they two share the same property, which is a two-state particle, two-state environment that they can actually have either 0 or 1, for example. But in the end, all you need is just two-state quantum systems. And in physics, there's so many of them. They are everywhere. These are just some examples. For example, you can use superconductor-based quantum computers, which is just superconductors. You can trap ions. You can use optical lattices. There's this idea of topological quantum computers is a little bit more mathematical, but it's really interesting too. Quantum dots on surface, nuclear magnetic resonance, gravity quantum electrodynamics. All these are like completely different fields, and people are actually actively studying and learning and figuring out how to isolate one qubit and how to couple all these 1, 2, 3, 4 or more qubits together in some amount of time that's going to be enough to just do some calculations. So, for example, to support my claim that progress is happening and it's every day, this is just like some news from like really recent news. 2015, IBM scientists are trying the quantum computer. There's this one in January that they were able actually to have 6 hours of coherence time, which is crazy. But it's just like a couple of qubits. But again, science is just happening, and for good or for bad. One of the leaks from Snowden was that NSA is building this. It seeks to build this quantum computer and invest $80 million in research, and this was 2 years ago. And they call this Penetrating Hard Targets Project. So I think my final remarks are the following. As we saw in the first slides, science takes some time to happen, right? Like it took 20 years to then to realize it's not only photons that share the wave particle duality, but it also matter. And the whole quantum mechanics, it took the entire last century to develop, and it's happening. It's still a lot of things to be learned. And even in the quantum computer, there are a lot of things going on. There are a lot of other things that I didn't even mention here. Several quantum algorithms, quantum circuits, like topological quantum computers, which is really cool. And several other concepts that I even didn't touch here. But I mean, I think the point is like don't fool yourself. There are a lot of scientists doing this. There are a lot of agents doing this, and this is going to be something that is happening. And I think it's nice to at least pay attention and try to be interested like a little bit in the concept. And I hope my talk helped you to grasp a little bit of these ideas. So this is the background, and now you decide. Thank you. Some questions? Yes. Yeah, this is a classical channel, yeah. Definitely. So this, okay, so the question is, Bob and Alice, when they are actually talking about they are agreeing on which basis they are doing the measurements, they need a classical channel, right, to talk. So, well, we go to the old story that, yeah, we can hack the classical channel. Of course, if you can, for some reason, actually modify this message, yes, it is a problem. Then what's going to happen is what Eve can do is just change the message to her base, and then she's gonna know Bob won't be able anymore to know what's the error rate, and then they can maybe think that there are no errors, and yeah, and then they agree that this is a safe protocol. Yeah. Well, Alice can always look back and see if it's right? So maybe one way of doing this is just making sure that after maybe after the message, Alice can just look back to her message. Yeah. Any other question? Sure. That's a really good question. I'm not sure if I have the answer, but one thing that's fact that program is going to change a little bit, right? Instead of just, instead of programming the way we do now with just regular bits, we're going to have to think about qubits. We're going to have to think that the fact that all the information is just available in one qubit, right? In the one superposition of states. And I have no idea, but I think the languages are going to be really, really fun to learn, honestly. Yeah. All right, thank you.